Today I'm going to talk about the re-identification risk in graph data, and in particular the privacy risk related to the graph structure. This is a work in collaboration with Aalto University in Finland and Technical University of Denmark. So, we all know that if we have a dataset, a tabular dataset of individuals, they are re-identifiable with their unique and main identifier. For instance, a social security number. However, if we remove the social security number, we all know that individual can still be re-identified with their features, such as the age and the city they lived in. In graph data, it's the same. Usually, we have nodes with features associated to them. What if we remove these features? Well, in graph, we are not done. In a graph, we are not done. In fact, there is still the graph structure that could pose a risk. In this picture, the node in the middle, highlighted in white, is the only one that has 5 friends. So it's identifiable by this feature. So we asked ourselves, how unique are we based on our social circle? So how many friends we have, which in network analysis is called the degree, the amount of connection that each node has, and the connection between these friends, which is called the neighborhood. And I'm going to talk about social networks, so graphs representing social connection, but this can be applied to any type of graph. So we wanted to study the uniqueness of neighborhoods, how many unique neighborhoods there are, and we wanted to study this as a risk estimation tool. Based on the network size, how many nodes there are in the network, the average amount of connections per node, so how many friends we have on average, or how many connections we have on average, and the network structure, because we know that graphs can be sparse, can be dense, can have local communities as well, can be random. So there is a whole field called network science that studies the structure of the graphs as well. And there are so-called graph models, that they are statistical models that you can generate graphs. So we can play with this model and generate data and see if, based on the structure and the size, something changes about the uniqueness of neighborhoods. So how many of these local unique neighborhoods there are. So first of all, let's start by this. What if everything was random? So what if we can generate a graph with a probability to connect 2 nodes of 0.5? Can we hide ourselves in the crowd? So we used a tool, a visual tool, that we called uniqueness maps, which is just a visualization tool, to visualize how many unique of these neighborhoods there are, how many unique local structure there are. And we have the network size, so the number of nodes on the horizontal axis, and the average degree, so the average amount of connection per node on the vertical axis. And the colors represent the intensity of the uniqueness of neighborhoods. So in red, it means that there are no unique nodes. And in blue, it means that all nodes have a unique structure, so they can be identified on the structure, right? And if everything was random, there is a hope, because as the size grows, the uniqueness goes down, right? But we can see that it's also influenced by the average degree. So the more connection we have on average, more connections we have on average, the more unique nodes there are. And the transition is very small. Unfortunately, human connections are not random. We organized ourselves in communities that are locally dense. So we used another model to generate graphs, which is called the random geometric graphs, which is well known to represent a bit better the social networks. Things change. In fact, the influence of the size is less. So when there are these local communities, the size matters less. What matters is the average degree. In fact, as we grow in average degree, the more unique we become. And it's actually pretty worrying because above 20, more or less, every node is unique, of course, based on this experiment. And it doesn't matter the size. It matters, but much less. But what about real data? These were models, right? So we plotted 30 networks as an example, real-world social networks of different kinds against these uniqueness maps. The line that you see, it represents this uniqueness 0.5, so the lines in the middle that was very tiny. And we saw that, in general, networks with a low average degree and have also low uniqueness, and networks with a very high average degree, so the amount of connection is big, they have a high uniqueness of neighborhoods. Okay, good results. What can we do about it? Well, we can do different things, but a very simple approach could be simply uniform edge sampling. So you sample the edges and you lower the average degree because you lower the amount of connections on average, so you lower the average degree. So lowering the average degree, you lower the uniqueness, and what this allows, since it's a uniform sampling, it allows for error estimation and correction. For instance, you can reconstruct measures based on the structure, okay? So measures such as the average degree, again, or the clustering coefficients, the number of triangles in a network. And you can estimate with the error if you also share the data and the data sampled and the sampling rate. But, okay, this is not a bulletproof tool. In fact, it needs to be used with caution. Other attacks are still possible if you have labels on the edges or on the nodes. Existing links are still there. What it means that it really depends on the use case, as was said in some other talks before today. It really depends what you want to do. If you're interested in the graph structure analysis, this could be a way. There are also other techniques to anonymize graphs based on differential privacy, node differential privacy, and edge differential privacy that, of course, you could consider if you're dealing with graph data. So what do we take home? Is that uniqueness of neighborhoods can be modeled and can be an additional tool for risk assessments. The models do a pretty good job to predict this uniqueness of neighborhoods. If there is a high average degree, even above 10, you can be in danger because the more friends you have and the higher the risk. And in real-world social networks, it doesn't work to hide ourselves in the crowd because what counts is the local structure. And if we have to develop anonymization techniques, we should also take the structure into account, which is very important. And this can be used in practice if you're dealing with graph data, but you do not know how much is your uniqueness of neighborhoods, but you know the average degree, then this can be used. In principle, the talks end here, but since I have some time, I want just to add that we did the same also for networks with multiple layers. So there are different layers representing different networks with some overlapping people. And you can define the neighborhoods in different ways. We call it non-inclusive and inclusive, depending on which layer, which people you include or not in which network, even if they are not your direct connection. And the aggregated neighborhoods uniqueness can be even higher than if you have multiple layers. So aggregating doesn't always help in this case. Anyway, if you are interested, there is a paper out on this. And thank you for your time, and thank you to my co-authors from the Technical University of Denmark and Aalto University in Finland.